Hi, my name is Jacob White. I am a Jansky Fellow at the National Radio Astronomy Observatory in Charlottesville. And today I'm going to be talking about a radio view of the circumstellar dust in EX Lupi post-outburst. So just a quick overview of my talk. First, I'm going to start out giving some definitions of what outbursting stars are. I'm going to talk a little bit about EX Lupi, the focus of this analysis, and the observations from ALMA and VLA that we used. Give some details on the modeling, where I just sort of throw some math equations at you, and then give the key results, and then summarize everything at the end. So outbursting protostars. So what does that actually mean? So these are young stellar objects that have undergone a rapid increase in brightness very, very quickly. So this is typically like a delta V of something on the order of 5 magnitudes, and it comes on very suddenly, like over the course of like days, weeks, or months. The prototype system is FUors. This began its outburst in 1937 and is still slowly fading. So systems that are like FUors are referred to as FUors, if you've ever heard that term before. So we think that these outbursts are likely due to something called episodic accretion. So what is episodic accretion? In T Tauri stars and their disks, it is well known that there's still accretion of material from the disk onto the central protostar. But at certain periods of time, this accretion can become significantly enhanced, and then that process can repeat over and over again, which is what we refer to as episodic accretion. Now, we may not know exactly what causes this episodic accretion, but there are lots of different theories for potential drivers of it. And these range from gravitational instabilities within the disk, stellar encounters with multiplicity, or something like magnetic fields of the protostar that can flip and then cause material to start rushing onto the star. But why is this significant? So if you have something that's increasing the central luminosity by such a large amount, that can obviously heat the disk, and that can impact everything from chemistry to grain growth to morphology. And that is directly impacting your planet formation environment. So it could also have significant impacts on the planet formation process. So EX Lupi. This is the prototypical EXor type bursting system. So if you recall, the FUors type systems are called FUors. This is its counterpart EXor type outbursting systems. So why is this one so special? So unlike FUors, this has had two outbursts that we've observed, and they've both been very short in their duration. So the first one that we observed was in the 1950s. It lasted about a year or so. And then the second one that we've observed happened in 2008. And again, it lasted for about a year or so. So this has a second class of outbursting stars that are named after EX Lupi. They have had multiple outbursts. They're typically a lot shorter. And EX Lupi is special because we've had a lot of observations of it before, during, and after its outburst. We've also had the benefit of observing it more recently, so we've had broad spectral coverage of those different stages as well. And unfortunately, a lot of these stars, these outbursting protostars, are very far away, and EX Lupi is relatively close at 158 parsecs, so we're actually able to study it in a bit more detail and get, resolve the disk in a little bit of detail within the disk itself. So this analysis kind of wanted to answer the question, how has the most recent outburst impacted the disk? The most recent outburst was in 2008, so it's been more than 10 years since it ended. What's going on in EX Lupi's dusty disk? Did the outburst have any change on the dust in an observable way? Can we make any conclusions about how it could impact the planet formation process? This is what we wanted to figure out. And to do that, we turned to ALMA and the VLA. So there was 4 data sets that we had here. We had ALMA 100 gigahertz continuum with about 1 arcsecond resolution. We dug into the ALMA archive to get 230 gigahertz continuum observations. These were previously published in Hales et al. 2008. And then we also have new VLA 33 gigahertz and 15 gigahertz continuum data. Quick spoiler alert, the 33 gigahertz data resulted in a non-detection. This doesn't necessarily mean anything about the disk itself. We only had one of the scheduling blocks obtained from what we requested, so the observations just weren't really deep enough to make any meaningful constraints on the disk itself. So what do we do with this data? Well, radiative transfer models. So our approach is to generate a radiative transfer model, convolve it with the beam of a given observation to make simulated observations. Now, the original approach was to fit all of this data simultaneously, but we found at 15 gigahertz, the flux was significantly higher than for a disk by itself, so we were unable to do that. So we had to split it up into what I refer to as the high frequency data with ALMA, and then the low frequency data with the VLA. So the high frequency data, we fit simultaneously with equal weighting. And then for the low frequency data, we took that best fit model from ALMA and extrapolated it to lower frequencies, and then fit a central emission source on top of that thermal disk. So for our radiative transfer models, we used RadMC 3D. The density profiles are outlined here on the right of this slide. We used a mix of amorphous silicates and carbon particles up to 10 millimeters in size. Remember that number. We use a standard gas to dust ratio of 101, size distribution of 3.5, and then a Metropolis Hastings MCMC modeling approach was used to constrain the radius, mass, scale height, and the disk profile. So let's look at some of the results. These are the results from the high frequency or the ALMA data. So here we have on the left, the data, in the middle, the best fit model, and on the right, the residuals. So this is for the 230 gigahertz on top and 100 gigahertz on bottom. So you can see that these models fit the data quite well. The best fit disk parameters are relatively in line with what was observed previously for EX Lupi post-outburst. But the big takeaway is that since we included grains up to 10 millimeters, and the ALMA 100 gigahertz data, which traces roughly the 3 millimeter grains, is very well reproduced. We have grain growth in here to at least 3 millimeters. So it could be larger than this. We can't really say without data at some slightly longer wavelengths, but that's pretty significant, and this could have been spurred by the outburst itself. So we also noticed that the ice line migrated. So during the outburst in 2008, the ice line in the midplane was between 1 and 2 AU. And then now in our best fit models, the ice line in the midplane appears to be between 0.2 and 0.3 AU. So that means it's migrated inward significantly in the last 10 years. So this is completely consistent with the thermal relaxation times outlined in Flock et al. 2017. And we find that there's been enough time for that heated disk from the outburst to cool off and the ice line move back inwards. So this is significant because an ice line can be a source of turbulence in a disk. So the areas just inside and outside the ice lines can get mixed up a lot, and you can have grain growth happening along that line. And if it's migrating outwards during the outburst and then back inwards after the outburst, you could potentially have a moving source of grain growth throughout the disk. And this could have actually been what spurred the larger grain growth to up to the 3 millimeter sizes that we inferred from the ALMA data. So that is our two big takeaways from the high frequency data: grain growth and ice line migration. So let's look at the low frequency results. So again, here we have the data, the best fit model, and the residuals. And just to remind you, what we have is this ALMA model, the best fit disk model, extrapolated out to 2 centimeters or 15 gigahertz. And then we fit a central emission source on top of that disk model. So the best fit flux for that central emission source is 55 microjanskis, which is a lot more than the disk itself. But what could be the source of that emission? So we try to do like sort of an exhaustive search of every possible source of something that could be that bright. So the naive assumption would be, stellar thermal emission, but that would require a brightness temperature of 10 to the 7 Kelvin, which wouldn't really be practical. It could be synchrotron emission. So if it was synchrotron emission, we would need sort of lightly to moderately relativistic electrons. with a magnetic field of about 5.4 kilogauss. So this is a bit higher than what was seen in the star previously. So, I mean, maybe this is it if the magnetic field has switched significantly in strength, but we want to explore what else there could be. So it could be gyrosynchrotron emission. So for it to be gyrosynchrotron emission, it would have to be coming from a pretty large area, about 0.3 solar radii. And optical spectroscopy has shown that there could potentially be some pretty large star spots on the surface of EX Lupi. And this could be from large accretion columns of material onto the star. And if this is the case, then we could have gyrosynchrotron coming from those sources. Now, there could also be radio jets or disk winds, but if that was the case, we would expect a relatively flat spectral index. And if we did have a flat spectral index, then even with our not as deep as we wanted 33 gigahertz data, we should have expected to see something, and we didn't see anything there. And there's no other evidence for radio jets in EX Lupi. Now, another potential source is free emission from X-ray heating in the accretion shocks. Well, we know that there's accretion going on, and we know that there's significant X-ray emission from EX Lupi. So this actually is another potential source of the emission. This could actually account for up to 10% of the total flux. So we think it's some sort of combination of gyrosynchrotron and free emission from the disk. So just to summarize really quickly, EXor and FUor type systems are outbursting protostars. We observed EX Lupi with ALMA and VLA. We recovered a good disk model of about 0.01 solar masses and a 45 AU radius. We see grain growth of up to at least 3 millimeters, possibly spurred by the outburst. And the ice line appears to have migrated inwards from 1 to 2 AU to 0.2 to 0.3 AU. And the significant emission at 15 gigahertz is likely due to non-thermal emission from either stellar gyrosynchrotron and or some free disk emission. Thank you.